So how can I imagine these initial fluctuations will leave? But it also tells you the radiation becomes the dominant force in the early universe. And in fact, is something that as an engineer or scientist, you know that as you compress the radiation, it gets hotter, and it also gets dense by the decrease in volume. The matter just gets more dense by the increase in the volume. So eventually, if you get small enough, the radiation comes to dominate over the matter. And that happens about when the universe is around 10,000 times smaller, and the radiation begins to dominate the whole universe. So the question is then posed, would fluctuations on a primeval fireball survive to an epoch when galaxy formation is public? Because you can't start forming galaxies till neutral atoms form, so they can start condensing to form galaxies. And so that's a sharp problem. So either this radiation came from the Big Bang, in which case it blows away the galaxies, or it's something after the Big Bang, and it's some spectacular process that happens later in the universe. So that's the problem that was posed to me that I saw when I was a grad student busy trying to get my PhD finished. And my colleagues who heard this talk or read the paper said, this is really fun. These guys aren't doing science, they're just guessing, right? And I said, this is a land of opportunity. This is a new market that we can exploit, right? If we have the technology and the engineering to do it, right? And so when the time came, when I got a chance, I came back to this field. Okay, so let me give you what is one of our #1 tools in the cosmic scene investigation, is that when you look out into space, you look back into time. And that's because light has a finite travel time. You're used to turning the light switch and the light goes off or on, and it seems like it fills the room instantly, unless it's fluorescent, it takes a little longer. But the light, when the light comes on, it takes, but if you think about light coming from the sun, so here's the moon, it takes 2 seconds. From the sun, it takes 8 minutes, right? From the nearest stars, it takes about 10 years. From the center of the galaxy, it takes around 30,000, 100,000 years. Right? So if I take a picture of the sun, it's what the sun was like 8 minutes ago. If I take a picture of the center of the galaxy, it's what it was like 100,000 years ago. If I take a picture of Andromeda Galaxy, the nearest big galaxy, it's 2 billion years ago. That's before humans were humans, right? So now what I have is a time machine. I take pictures, right? Light is this time, it's a storage device. It takes this long time traveling across space, and it's storing an image of what was going on in the universe at the previous time. So as I go out, I can get out past 10 years, I can get to thousands of years, I can get to millions of years. I can look at the sort of the distant galaxies in the Hubble flow, and that may be up to 10 billion years. But if I look to this relic radiation from the beginning of the universe, that's 14 billion years ago. So if I could take pictures of various things whose distance I knew, then I could make a time-lapse history of the development of the universe. Right? So that's my #1 tool, is distance equals time. Light travel time. So the natural units are billions or light years and years, right? That's the natural units. Getting rid of the speed of light is the natural units of connecting space and time. Okay, so here, without all the coordinates, here's a picture of what we think the universe might be. Look how we would see it. Near us, we have a pretty mature galaxy, the one we're in, but around us, or in the sphere around us, they're fairly mature galaxies. But if I look out further, they're the developing galaxies. And if I look out far enough, I see back to the very beginning of the universe. And so again, I've suppressed one of the dimensions out of stuff, but you have to imagine all 3 spatial dimensions there. And I'm taking into account there's what we call the past light cone, that I can only see things from a certain time epoch and so forth. So this is the idea, and you have to imagine a complete sphere around us, that as I look out, I'm seeing different epochs. And it's not to say that this region out here hasn't gone on and progressed. I'm just seeing it back at this ancient time. Okay, so I now go to my CSI handbook on evidence and use the tools of trades and procedures. And I look under the handbook, and I look for the thermal imaging camera. And I would use the thermal signatures rather than optical light to create a photo or an image or a video of the early universe. Well, the universe doesn't change very fast on a human scale, so images are what I usually make. And so that's the technique that we're trying. So here's the beginning of the tools of trade. So here is the time period, 1967 to 1969. Dave Wilkinson, who was one of the original people that were tasked to start looking for this before Pincus and Wilson beat him to the punch by a couple of years. Here are the beginning instruments for looking at that. And so as I was telling some of the students this morning, we started developing the technology you have one horn that looks at the sky, one horn that looks at a reference load, and you do the difference between the sky and the reference load to measure the temperature, or you do the difference between two parts of the sky to measure what the variations are in the sky in terms of what's going on. So this shows what it looks like when it's brought out to be assembled. Here's the assemble setup at White Mountain, a screen to try and keep out the unwanted ground radiation, the sky horn, and then a reference horn that looks at in this case, a liquid nitrogen coal load. Later on, liquid helium is what people are using. That's why Pizzi and Wilson were able to do it, because Bell Labs had put a liquid helium coal load that they could use with Telstar antenna and so forth. So we started developing the technology in the 1970s. So my group, I stopped doing the other experiments I was doing, which were looking for antimatter in the universe and some other things, and moved into studying the microwave background radiation. So we decided we had to develop a very sensitive instrument to look for these fluctuations that were eventually going to grow into galaxies. And we needed fluctuations at the time. We thought there were about a part in 1,000 of the radiation. That is about 1,000th of a degree fluctuations out of the 3-degree Kelvin, right? So roughly a part in 1,000. And so we had to develop a system, and we used the differential measurement. You compare two parts of the sky with two identical antennas. You switch very rapidly between those two antennas at the input of a whole very sensitive receiver chain, and you look for a signal that's changing synchronously with the switching back and forth. So you don't measure the absolute temperature of the sky to a part in a million here and the absolute part to a part in a million here. You measure the differential between them sort of instantly by doing a lock-in amplification there. And so here's the first prototype in the lab. Here it is shown in the first apparatus we built. So this is a 1 centimeter wavelength system with corrugated horn antennas to control the side lobes and everything very carefully. And this is a 0.5 centimeter wavelength one to monitor the atmosphere. This whole thing is mounted on a rotating table because we had to make sure the two antennas and the equipment were identical. So you had to be able to take this look at this part of the sky and this look at this part of the sky and exchange them so that they were swapped which part of the sky they're looking at. The signal from the equipment you hope didn't change. The signal from the sky should reverse because you're comparing one side to the other. So, and then you turn the airplane around, you do a whole series of things like that in order to make this work. And so you have it in the rotating table, you seal it against any RF interference, and you have only the windows you can look through with quarter wave or directly in the antennas. You cover it so that it's covered hatched, and you'll be able to store it at 90 degrees so when you take off and land that no dirt gets in. And when you put it in the top of a U-2 airplane, and none of you are old enough to remember what a U-2 airplane is, but it used to be famous for flying from Turkey to Scandinavia and taking beautiful pictures of things on the ground until there was an incident when one of them landed in the Soviet Union, and President Eisenhower was very embarrassed. And then some of these were made available to the civilians to be able to take pictures of crops and seashores and land use and so forth. And so there were a lot of instruments designed to look down, so all these, and then one instrument designed to look up at the sky, and then we got to fly in the airplane to do it. Here's Mark Gorenstein as the first graduate student to get his thesis on this experiment. Here's the equipment sitting in there. There's an airplane. It's a beautiful engineering design. Clarence Kelly and his Skunkworks team did this. It's the first wet wing aircraft. So you'll see it has these two pogos because it droops until it starts moving and the pogos fall off. And then it's a bicycle wheel. Has tremendous lift. It flies very high, flies much higher than Jet Airlines, about a factor 2 higher, and very stably. We measured that it was flying level to less than 1/6 of a degree. And we did a lot of things like that. So it's a very spectacular engineering feat, made it possible for us to do our job. Okay, so we ended up making this map of the sky. So here is a map of the sky, and this is such ancient days, we didn't have good computer graphics. We had to do some of the graphics by hand, and so that's why there's contour lines in here and so forth. But we saw it roughly in this direction in the sky. It was warmer by about 3,000th of a Kelvin. Right, 3 millikelvin. And then the opposite, it varied smoothly to the other direction to minus the same amount, so roughly 1 part in 1,000. And that's easy to interpret if you think about the Doppler effect. If you're driving through the rain will hit the windshield harder than it will hit the back of your car because you're collecting a lot more volume. You also get a frequency boost from driving, from the Doppler effect. And so the temperature goes up. The collecting goes up when you go in the direction you're going. It makes it warmer, and it makes it cooler in the direction you're leaving. And it's not surprising because we knew, in fact, that the galaxy is rotating, that the Earth's going around the sun, the galaxy is rotating. So we expected roughly a part in 1,000 the speed of light. This is just the wrong direction. So I show you this picture that we made up later on for the COBE satellite. Here's the Earth. We were flying out of Ames.